Hooke's law is simply the relationship between how far a spring is stretched and how much force the spring exerts. And in our spreadsheet lab we just finished, we found that the relationship between force and displacement was a linear relationship. And if we take a spring and stretch it a little bit, we get a little bit of force. But the more and more and more we displace the spring, the more and more force the spring provides. And it is a linear relationship. Y equals the slope times the x plus the intercept, and the intercept was 0, so we have the force is equal to some constant times the displacement. That constant is known, well, it's the slope of the line, but it's known as the spring constant. If you had a really stiff spring, that would be a big number, because if we displaced it a little bit, multiplied by a big number, we would get a lot of force. If it's a really thin, light, very stretchy spring, the spring constant would be a lot less. So if we displaced it some amount, we would get very little force. And so when the spring is in its natural position, not being pulled or pushed, we'll call that its initial position. And when we push and compress that spring in the positive direction, the force that the spring exerts is going to be back to the left. The person was pushing the spring to the right, but we're talking about the force of the spring that was back off to the left in the negative direction. And if we stretch that spring off in the negative direction, well, the force is going to be back in the positive direction. So force is a vector quantity, so is displacement. So the force of a spring, we have a arrow over the top indicating that it really does have direction. And we showed you before that this was the force equals kx, but sometimes you see a negative sign there. It just means that if the x is positive, we put it in the positive direction, the force would be back into the negative direction. So a positive number here multiplied by a negative would give you a negative force back off to the left. And if we had a positive, or if we displaced it to the left being negative, it would have a force back off to the right, which was positive. So a negative number times a negative number results in a positive number. A lot of times you'll also see this equation written this way, where we really aren't going to keep track of positives and negatives. We're just looking at the absolute value of the force and the absolute value of the displacement. So we just always know that the displacement will be in the opposite direction of the force of the spring. Not the force that the person is pushing on it, but the force that the spring is providing. So yes, the person was pushing to the right, but Newton's third law says the force that the spring provides is going to be back to the left. And it was discovered by Robert Hooke. And an interesting thing about Robert Hooke is that he and Isaac Newton did not get along. Isaac Newton thought that Hooke was dishonest and didn't give credit to Newton for some of Hooke's discoveries. And this is a painting of Robert Hooke. Now, Hooke died in 1703, and this painting was done in the year 2004, almost 300 years later. But the reason the painting was done is because no portrait of Robert Hooke survived the 17th century. Possibly because the portrait that was painted of him was hanging in the Royal Society, for which Newton was the chair. And I think it's possible, I don't want to assume, but Newton disliked him so much that Newton had the portrait destroyed. And so this is a painting of him based on descriptions from two of Hooke's colleagues that were written during his lifetime. So we don't really know for sure what he looked like. You could go to a website and buy springs. And there's lots of different kinds. There's compression springs, so you push them together. There's extension springs, you pull them apart. Torsional springs would be twisting. And conical springs are just compression springs typically that are allowed to, the coils don't get in the way of each other, and they can compress a good distance there and get into a very short, small space. When you buy the springs here, you can buy the spring at a certain length, diameter, material, but this column here is the rate. And so, for example, this spring here has a rate of 2 pounds per inch, and that's the spring constant. So if we only displaced the spring ½ an inch, that spring would only push back with 1 pound. If we stretched the spring 2 inches, well, it's 2 pounds per inch. If we displaced it 2 inches, the spring would have pulled with 4 pounds of force. And I should say also that springs have a limit to where this is true. You can overstretch a spring beyond its elastic limit, and this relationship wouldn't follow anymore. It wouldn't be a linear relationship, and you would ruin the spring. You would overstretch it. Okay, so here are 5 different springs, and they're all at this initial length. And when I put some weight on there, this spring stretched a lot. This spring stretched a little bit. If I put twice as much weight, they stretched twice as much. But which of these springs has the larger spring constant? Which of these has a bigger number there? Well, it's going to be the one that displaced a shorter distance. They all had the same force, but the shorter distance of displacement got the same amount of force because the smaller distance had a bigger spring constant. In fact, this is the spring constant for each of these. Okay, 25 newtons per meter. If I had stretched that a full meter, I would have gotten 25 newtons of force. And one of the big things about Hooke's law, and the really neat thing, is that it is a linear relationship. So here is a spring scale, and the spring constant is calibrated such that if this displaces that little distance there, well, then you must have put 1 kilogram on there. If it displaced down to here, twice the distance, well, you put 2 kilograms on there. It's a linear relationship. The displacement of the spring is linear to the amount of force that was applied to it. And a neat application of that is if you're in a cafeteria somewhere and you have to pick up your plate from this dispenser, you may have noticed that if you pick off 1 plate, it goes up by a little bit. And you pick off 5 plates, it goes up by the height of 5 plates. And that is solely because the relationship between force and displacement is a linear relationship. So we have the displacement is going to be the thickness of the plate. Okay, so 1 thickness results in 1 weight. Well, if this is Hooke's law, the spring constant is the force of the spring divided by this displacement. So we just need to choose a spring constant where the weight of 1 plate divided by the thickness of 1 plate equals the spring constant. And then you remove that weight, it moves up a little bit. Remove the same amount of weight, it moves up the same amount because it's a linear relationship. Now we can relay this back to friction. And I guess maybe one thing I should say is that with the unit of dynamics, it all deals with how force affects motion. Friction is something that provides force. Well, springs are something that provide force. And we can see how it relates to motion. So in this example, we're going to have this truck here slowly push against this spring and compress this very heavy-duty spring. And it's going to push against this very massive boulder, and we would like to find the mass of the boulder. We know the coefficient of static friction, and we know the spring constant, how stiff that spring is. And then as we push this together, friction is going to get more and more and more and more, but there's a limit to how much friction you can get. And right when that spring was compressed, 0.72 meters, the boulder was finally able to budge and begin sliding, and that would be kinetic friction. So The force of the spring equals the spring constant times the displacement. The force of friction adjusted to try to keep it stationary, but there was a maximum value that it could be, and it was equal to the coefficient of static friction times how hard those two surfaces were pressed together, called the normal force. And the thing here is to see is that when it finally breaks free, the force of the spring was exactly equal to that maximum amount of force of friction. So then we just substitute things in here and here. The notation with the vectors here and the absolute value can get maybe a little cumbersome, so I'm just dropping it off there because we're just plugging numbers in. We're not doing anything real crazy with vectors here. So the spring constant times the displacement is the force of the spring, and the coefficient of friction times the normal force, because the ground is level here, it's just the weight of that boulder pushing against the ground, and the ground pushing back equally is what the normal force is. Okay, so the whole question here is find the mass of the boulder. There it is. So if I divide both sides by the coefficient of static friction and divide both sides by the acceleration of gravity, that would be the mass. So this was the spring constant. That's how far it had to be compressed or displaced. This is the coefficient of friction and the acceleration of gravity. You plug all those things in and multiply them out. Looks like that boulder is going to be 1.6 metric tons. Imperial ton is 2,000 pounds, and a metric ton is 1,000 kilograms. Sometimes springs are put in parallel with each other, so two side by side, or springs can be put in series with each other, one after the other. Now in this example, each spring is identical. So these two, that one, and those two are all identical. And we're going to put some force on the spring. So the force of gravity is pulling down, but the force that the spring applies is back in the up direction. So this weight is going to pull the spring down some distance, but that weight here is pulling against two springs, so it only pulls it half the distance. This weight, half of it was held by this spring, half of it was held by that spring, so it's only going to, half as much force is only going to stretch it half as much. But here, when the springs are in series, the same amount of weight is going to displace it twice as much as what this was. So this weight here stretched the spring 1 unit, and it had a spring constant of K. This only displaced it half a unit, and that's because the spring constant was 2K. Here's what happens. The same amount of force only stretched it half the distance. That means the spring constant must have been twice as much. So the effective spring constant, with two of them in parallel, would be twice what one of them would have been. Over here, this one got stretched twice as far as what this did, and that's because whatever force this weight puts on the spring, that force is tension that goes through the whole thing. So if I had just had that one on here, it would have stretched it this far, because this force stretched it this far. That same force is going to stretch one spring that far. But the other spring would have stretched that distance as well. That's why the same amount of force stretched it twice the distance. Each spring stretched this distance. So with the same amount of force, if it displaced it twice the distance, the spring constant must have been half what it was here. So springs in parallel, you double the spring constant. Two springs in series, you have the spring constant. All right, let's see how you can apply that to here. This is a Ram 250, and the maximum payload for that would be 3,000 pounds. and the maximum spring displacement would be 10 inches. So you put a bunch of weight there, it compresses these springs, and you still need a little bit of travel in those springs, so if you hit a bump you don't bottom out. But we'll say that the maximum displacement is 10 inches. What should the spring constant be? So if you're going to put coil springs in your car, what spring constant do you choose? Well, the force of a spring is spring constant times displacement. So this force would displace it this much. So it looks like the spring constant should be 300 pounds. Okay, that's not what one of these is. There are two springs, one for this tire and one for this. I am assuming that this weight is solely on the rear axle, that it's really not affecting the front axle. So if the combined spring constant needs to be 300 pounds per inch, one of those springs must have only been 150 pounds per inch. I hope that clears up Hooke's law and spring constants and displacement. That is it.